Have you ever looked up at the night sky and wondered? There it hangs, a silent, silvery companion on our long journey through the cosmos. The moon. It pulls at our oceans, lights our darkest nights, has inspired countless stories, songs, dreams. But what if I told you that this familiar friend holds one of the greatest unsolved mysteries of our solar system? Its very existence is a puzzle written in ancient rock and starlight. How did it get there? Where did it come from? This question has haunted scientists for centuries, a cosmic whisper that we're only now beginning to understand. The answer, it turns out, is more violent and more spectacular than we ever dared to imagine. For a long time, we thought we had a good idea. We called it the giant impact hypothesis. The story went something like this. Long ago, when our Earth was just a baby, a Mars-sized object we nicknamed Theia smashed into it. The collision was catastrophic. It threw a colossal amount of molten rock and debris into orbit around our young planet. Over time, gravity, the master sculptor of the cosmos, pulled all of that rubble together. It clumped and spun and cooled, eventually forming the moon we see today. It was a neat story, a tidy explanation. But like many neat stories in science, it had a few nagging problems that just wouldn't go away. The biggest problem was a chemical one. When we brought back rocks from the moon, thanks to the Apollo missions, we expected them to be different. They should have been made mostly of material from this mysterious impactor Theia, but they weren't. Instead, the moon's rocks looked suspiciously like Earth's rocks. They shared the same chemical fingerprints, the same isotopic signatures. How do you build a time machine? Not with flashing lights and spinning dials. Our time machine is built from silicon and software. It is a supercomputer. These machines are our portals to the past. They let us use the fundamental laws of nature: gravity, thermodynamics, fluid dynamics. Then we simulate events that happened long before we were here. We can input starting conditions like a young Earth or a colliding planetoid, then tell the computer to calculate what happens next, one tiny step at a time. It's like creating a virtual universe inside a box. These aren't your everyday desktops. These simulations are among the most complex ever attempted. Machines that can perform quintillions of calculations per second. That's a billion calculations. The supercomputer finished its work, the digital dust settled, and the scientists watched the movie of our moon's birth. What they saw was honestly just breathtaking. In these new high-resolution simulations, the story unfolded not over months or years, but in a matter of hours. The Mars-sized Theia didn't just deliver a glancing blow, it slammed into the young Earth with devastating force, a cosmic haymaker that nearly shattered our world. The impact was so violent that it instantly vaporized and melted huge portions of Earth's mantle and the impactor itself, creating a swirling, incandescent mess of rock and gas. The simulations showed that a large, self-gravitating clump of matter, the proto-moon, was thrown into a wide, stable orbit almost instantly. It was as if the impact itself gave birth to the moon in a single, fiery push. This new understanding is more than just a minor tweak to an old theory. It is a fundamental shift in how we view the formation of our closest celestial neighbor. It's like discovering a new dramatic first chapter in a book you thought you knew by heart. The moon is not just a collection of leftover rubble from a cosmic fender bender. It is a direct, substantial piece of the primordial Earth, hurled into the sky during the most violent event in our planet's history. This makes the moon less of a companion and more of a sibling, forever linked to us by a shared, fiery birth. The impact that formed the moon wasn't just a side story. It was a planet-defining event. The sheer energy of the collision would have melted Earth's entire surface, creating a global magma ocean thousands of kilometers deep. Furthermore, this high-speed formation scenario has implications that stretch far beyond our own cosmic backyard. If a moon can be formed this quickly and violently, it might mean that large moons are more common in the universe than we previously thought. This new model suggests that a wider range of catastrophic impacts could result in the formation of a stable, large satellite. So the next time you gaze up at that luminous orb in the night sky, see it for what it truly is. See it not as a cold, distant rock, but as a piece of our own world, a testament to the violent and creative forces that shape the cosmos. It is a scar and a monument, a ghost of the Earth that was, and the partner that allowed our planet to become the haven for life it is today. The mystery of its birth, a puzzle that endured for centuries, has been unlocked not by a telescope but by our own ingenuity, by our ability to recreate the universe inside a machine. This journey of discovery is a perfect example of the scientific process at its best. But does this mean the story is over? Of course not. This is science. Every answer opens the door to a dozen new questions. The birth of the moon is just one tale, one chapter in an infinite cosmic library. There are countless other mysteries waiting for us out there in the dark, and that journey has only just begun.